Okay. Hi, welcome to our event at the Cryosphere Pavilion today. We'll be talking today about what does the extreme low sea ice in 2023 tell us about Antarctic's future. Today we'll have three speakers here: Sean Henley from University of Edinburgh, Stephanie Arndt from AVI, Alfred Wegener Institute, and Won Sung at the Korean Polar Institute. And I'll pass off to Steffi now. Thank you.
Yeah, thank you. Yes, and welcome also from my side. I'm really glad to open this presentation on behalf of a huge international and interdisciplinary group, as you can see here on the first slide. Even though we are only 4 speakers, we are glad that we have quite a big team behind us who prepared this presentation with us. When we talk about sea ice in general, in previous years, when we looked into the polar regions, the main focus was always on the Arctic sea ice, given that we had there quite some changes and a lot of stuff going on in terms of sea ice retreat. However, when we now look in recent years, also in the Southern Ocean, we just discovered this year a huge change in the Antarctic sea ice cover, which really put us on alarm. And this is why we want to use this opportunity here at COP to talk not only to science, but also to the public to point out why it is important to talk about the topic. So therefore, let's have at first a look onto the evolution of the Antarctic sea ice extent over the past years. And you can see here now the sea ice extent from January to December, whereas you can see in the gray lines the sea ice extent anomaly, meaning how it changed with respect to the overall mean over the last decades. And in the red line, you can see the anomaly for 2023. And what is pretty obvious here that this anomaly is not only a normal anomaly, but this is really far below everything what we observed before. So therefore, let's dig a little bit more into detail here now, what has changed over the past years. So therefore, here you can see again the anomaly, however, now as a time series over the past 45 years. And you can see that we had always strong interannual variability in the Southern Ocean, with even slightly increasing sea ice extents towards last decades. However, now in 2016, there was a first change in the whole evolution. However, this evolution was mainly seen in summer years, in summer times, and the sea ice cover could always kind of recover again during winter times. However, now looking into 2023 again, this really highlights a big change, not only with regard to the summer sea ice extent, but also with regard to the winter sea ice extent. So unfortunately, the sea ice extent could not really get healthy again during winter time, and this is why we are really concerned and why we are happy to have the opportunity here to dig more into that topic. And with that, I hand over to Ron.
Thank you. Right. My name is Won Sung from Korea Polar Research Institute, and then I'm going to talk about the importance of the sea ice and then there are global impacts. Let's begin with the Earth's energy budget. Sea ice reflects, as you see here, reflects sunlight back into space, while dark ocean absorbs more of it. And recent studies indicate that the loss of Antarctic sea ice changes the Earth's energy budget. The ocean absorbs more energy, leading to increased temperatures, in turn cause more sea ice to melt. This creates a loop. We call that positive feedback. Sea ice also influences global sea level rise, which is really important and significant. Although its impact is indirect because it's already floating like ice cubes in the glass of the water. Here we present the various forms of the ice. We classify ice by looking at them where they are. So ice sheets lying at top left-hand side in the figure. The Antarctic continents flow towards the ocean. Once the ice starts to float, there is a ground line which ice, ocean, and the ground meets together. We call it grunt line, and we call it an ice shelf in the middle of the figure. The mass loss of the ice sheets directly contribute to the sea level rise, and ice sheets are restrained by fast floating ice shelf there. And then so when these ice shelves thin by based on melting, or the ice front calving by several physical processes like ocean storms or the ocean swells or the big tsunamis from the northern hemisphere as well, they lose back stress, then which can accelerate global sea level rise in turn. So sea ice being frozen the western side there, being frozen seawater does not directly contribute to sea level rise, but plays a protective role for ice shelves and therefore ice sheet as well. As mentioned earlier, there are two major physical processes weakening the stability of ice shelves. One is basal melting, as you can see here. Probably in the summer season, the absence of sea causes ice shelves vulnerable to ocean swells or tsunamis, as I mentioned earlier, causing more instability. Remember, the darker the ocean surface absorbs more solar energy, leading to warmer surface water, resulting in less sea ice in the summer season. In winter, the freezing of sea ice creates a cold, dense, and salty layer of water that sinks to the bottom, finally protecting the ice shelves from the intrusion of warm, deep water underneath the ice. Note that 2023 has been marked by the record low summer cover and also record low sea ice formation. One very low summer is enough to trigger a rapid retreat, but if years like 2023 become the normal, it will continue and increase the risk of rapid ice shelf loss and therefore acceleration of sea level rise in the future. We're not used to seeing the world like this way, but it clearly demonstrates that the Southern Ocean is central to the global ocean system. The Southern Ocean has been playing crucial roles in modulating ocean heat and also carbon uptake over years because of its unique connection between the surface and the deep waters of the Earth. Sea ice is an essential component of that link. The enormous freeze and melt cycle, as you can see here, drives a pump that circulates heat and nutrients between the surface and deep waters and controls in exchanging energy between atmosphere and ocean in the Earth system. The reduced sea ice production observed in the Austral winter this year threatens to diminish that service and can continue on the warming world that we are experiencing now. And now let's move on to the impact on surrounding ecosystem.
Thank you, Wansang and Steffi, for a fantastic introduction, and thank you for joining us in the room and online. So I am Dr. Sian Henley. I'm a reader in marine science at the University of Edinburgh, and I also represent the Southern Ocean Observing System. But I'd also like to acknowledge great support from Dr. Nicole Hill in preparing this part of the presentation. And Nicole is online for the panel discussion at the end. So thanks, Nicole, and thanks for joining at Wednesday evening Australia time. So yeah, I'm just going to say a little bit about why sea ice is important for the ecosystem, and then I'm going to go into more detail about how the two recent low sea ice extents have been particularly damaging for the ecosystem and what this signals as we move forward in a warmer world. So sea ice is important for ecosystems for two main reasons. That is for the ecosystem that exists within and around the sea ice itself, but also the role that the sea ice has in structuring the oceanic ecosystem by influencing the physical and chemical properties of the ocean that supports a vast array of life. So this first slide shows at the top a picture of the sea ice system, and on the left-hand side, and then on the right-hand side, the structure of the sea ice. And what it shows is that sea ice can host a vast array of life. So when we look at the sea ice and we see that it's basically white, we might think that it is rather devoid of life. But in fact, as the images on the bottom here show, sea ice actually harbors a hidden forest, an absolute abundance of life. And this forest is made up of microscopic plants or algae, which provide a food source for the entire ecosystem. And from the picture on the right, you can see that the sea ice also has a very complex physical structure, and this provides a habitat or a home for young Antarctic krill, where they spend the winter and can then complete the first important year of their lives, and then can mature and grow into adult krill, which is a key food source for lots of the animals in the Southern Ocean that we recognize as iconic species, like the penguins, the whales, and the seals. So with the sea ice loss that is occurring, there is great concern that we will lose this component of the wider Southern Ocean ecosystem, and therefore will lose a critical food source at a critical time of year that really provides the base level of the entire ecosystem. And we might see significant changes in the structure of the ecosystem and the way that it functions as a result. So this image here shows how sea ice influences the animals and other organisms living within the water itself. And we can see that the sea ice on the left-hand side of the image provides a source of sea ice algae in yellow, and it also provides a source of fresh water and iron, which provides ideal conditions for the phytoplankton bloom, that big green blob in the middle there, which provides the foundation for the ecosystem. So this phytoplankton, or microscopic plants, take up a huge amount of carbon in a process named photosynthesis. And during this, they produce large amounts of biological carbon, as well as producing oxygen and making the ocean a healthy place to live. When these phytoplankton, or the ice algae, are consumed by Antarctic krill, copepods, and other species that graze on this mass of food, they transfer carbon to these animals. And then in turn, when the copepods and the krill are consumed by the whales, seals, penguins, fish, squid, this carbon is passed up the food web and stored for timescales that are relevant for mitigating climate change. And then when these organisms die and sink to the seafloor, or when they're still alive and they excrete, they also transfer carbon downwards in the water column, where it can be stored for longer periods of time and therefore play a more important role in mitigating climate change. So all of this is to say that Antarctic sea ice supports high amounts of biological productivity, which are important in providing a natural means to mitigate climate change and supporting the high biodiversity that is important both within the Southern Ocean and throughout the wider global ocean, because lots of species that live in the Southern Ocean migrate north and south on an annual basis. So the changes that we're seeing in Antarctica, particularly with respect to the sea ice lows that we've seen in recent years, have influence throughout the global oceans. And this slide here shows how the changes in sea ice can cascade through the entire food web, because changes in the lower trophic levels, like the phytoplankton, the krill, and the small fish, have implications for the animals that feed on them, like the penguins, the seals, the penguins, and the whales. So we don't yet have a very good understanding of how changes in sea ice cascade through the ecosystem, but we do have some evidence from the West Antarctic Peninsula that has seen dramatic declines in its sea ice extent over the recent decades. And here we've seen that phytoplankton species composition can be changed, Antarctic krill distribution can be changed, and in terms of the penguin species, there are species that are specially adapted to the cold, more Antarctic-like environment, which are suffering. There are other penguins who are normally further north, which are actually benefiting from the warmer, more ocean-like conditions that are now found at the Antarctic Peninsula. So this gives us some indication of changes that might happen around Antarctica if we continue to lose the sea ice on a seasonal basis. But really what we need is to increase our continuous research and monitoring, and we need to upscale our efforts so that we can better understand the changes underway and manage them as effectively as possible to ensure that these ecosystems are sustained as effectively as possible in a warming world. So at the Antarctic seafloor, there is also a huge amount and diversity of life. When conditions are favorable, you can see scenes like this one on the screen here, with large amounts of sponges and corals and other seafloor species. Now, these are reliant on food coming down from the water column above them in the form of phytoplankton or ice algae that have sunk out of the surface waters. So this means that what happens at the surface of the ocean related to the sea ice also has strong implications for life at the seafloor. Now, as sea ice declines, we also see an increase in the amount of movement of icebergs in coastal regions. And when icebergs crash into the seafloor and then move around, they grind up the seafloor and destroy any ecosystem in their path. So this has a very negative effect on the biological communities on the seafloor. Whereas when we see sea ice retreat, we see there is more area of the surface ocean that is available for phytoplankton blooms, and therefore these systems increase more food, receive more food. So there is a competition, if you like, between the positive impacts of more food to these seafloor ecosystems and the negative effect of more physical damage and disruption by icebergs. And these two effects are competing against each other to influence the amount of blue carbon, the amount of carbon that these ecosystems can store on timescales that are relevant to climate change, and the timescales of human impacts on the planet more widely. So when we shift our attention to the most recent sea ice losses in 2022 and 2023, we don't have much evidence of what that will do to the system yet, because these events are only just happening and happening now. But there is some evidence from the Bellingshausen Sea region, which sits at the southern end of the Antarctic Peninsula, which shows that emperor penguin colonies face a dire outlook as a result of these changes in sea ice. So the map on the left here shows in red, the more red the color, the lower sea ice was in comparison to its long-term average. And we can see that there are 5 colonies in this region. So on the right-hand side now, on the video, we'll play it through once, and then we'll go back to the beginning and pause so I can explain. We can see the, okay, so if we hold it there, thank you, we can see that the brown stain on the sea ice is the product of penguins. So it's a stain of penguin poop that has come from the colony, and it indicates that there is indeed a penguin colony there. And the penguin colonies form to raise the young, and the penguins, when the environment is suitable, have a period of crashing where the young are on the sea ice, and then a fledging stage where those penguins go into the water and swim off and live their happy penguin lives. But as we lose this sea ice, we're seeing that the sea ice is retreating before the penguins are ready to be to go off into the water and begin their adult life cycles. So we can see here the video running from October to December in 2022. And what we can clearly see is that as the sea ice disappears, the penguin colony is, the sea ice disappears around the penguin colony in around November. And usually the penguins would not yet be ready to fledge at this stage. So this suggests that the penguins are losing the platform that they need to sit on before they're ready to go into the water. And if this happens, the penguins drop into the water before their adult feathers are ready. And this means that the penguins do not have the appropriate waterproofing. And this means that they simply freeze to death because of the cold Southern Ocean waters. So we see dramatic breeding failures in years when the sea ice retreats too soon. And this happened in 2022 when these results were gathered by our colleague Peter Fretwell and his colleagues. Peter is based at the British Antarctic Survey, and this study really provides the first evidence of how this iconic species might be impacted by ongoing changes in Antarctic sea ice, and certainly has been impacted in 2022. And we know that of those 5 colonies in the Bellingshausen Sea, 4 of them were lost before the fledging season, that season when the chicks are ready to go. The colonies had, or the sea ice had disappeared before that period had started. And this suggests that the vast majority of those chicks were lost. So catastrophic breeding failure in this year. But this study looked at a fairly well-defined geographic region in the Bellingshausen Sea. And what we know a lot less about is the changes that happen around Antarctica, where we don't have the evidence that's been published in the West Antarctic Peninsula region. But this plot here shows the pink line is the long-term average of how extensive the sea ice is in February. And the white shading shows the sea ice condition in February 2022. And what we see is that there are vast swathes of the Antarctic coastline that would normally have sea ice that the penguins can use for their breeding cycle. But in this year, that sea ice was completely or almost completely absent. So this is likely to be a much more widespread issue, and indeed to affect penguin populations all around Antarctica. And so that was last year, that was 2022. If we come forward to 2023, as Steffi introduced at the beginning, this year has even lower sea ice than 2022 in terms of its winter extent. And the way that the trend is continuing very strongly indicates that in summer 2023, which we're currently coming into, we are likely to see sea ice cover that is as low as in 2022, or possibly even lower. And this raises the question of how many successive years of these very difficult conditions and widespread breeding failures this iconic species can survive. And I'll leave you with that question as we hand over now to Dr. Will Hobbs, who is joining us from the University of Tasmania in Hobart and is on the live stream. So Will, over to you.
Thank you, Sian. And I'm hoping you're going to move the slides forward for me. So as Sian said, I'm joining you from Nipaluna, Hobart, on the very edge of the Southern Ocean, where I'm a sea ice researcher at the Australian Antarctic Program Partnership. And I'm going to discuss the important question of whether the events that my colleagues have described in 2023 are a response to human greenhouse gas emissions. Now, it's a very difficult question because attributing any individual climate event, even one as extreme as this year's Antarctic sea ice, is very complicated and requires a really careful comparison of observations and climate models. Processes like the IPCC have a very high evidentiary bar to make those kinds of statements. And as yet, the scientific community is unable yet to make a definitive statement regarding the role of humans in this particular event. However, we do see changes in the behavior of Antarctic sea ice that really predate 2023, going back even 15 years, that are really important indicators of change in the system. So we've already seen this, this image of the satellite record of sea ice anomalies, with blue showing more ice than usual and red showing less ice than usual. And we've seen those changes in the mean state, the long-term increase and that very sudden drop-off to that mean state. But as well as the changes in the mean state, there are some other more subtle statistical differences that are really interesting for us to point out. So the first thing is we know that after 2006, which is shown by that red line, the variability of the sea ice has actually really increased. So you can see that the peaks and the troughs, which just sort of the fluctuations around zero, are much, much bigger since 2006. And in fact, the variance has more than doubled since that time period. We also know that the system has become more persistent. So what that means is that this anomalies tend to hang around for much longer. So you can see that generally in the earlier part of the period, you get a blue or a red period and it just straight away goes back to zero. But since in the last decade or so, whether they're positive or negative, anomalies are hanging around for much, much longer. We call this an increase in the persistence. And a really clear example of this is the relationship in the sea ice from one summer to the next. Now, historically, if you took the sea ice conditions from, say, 1980, it would tell you almost nothing about the summer of 1981. There's just no correlation from one summer to the next, because due to really interesting but complex ocean and sea ice processes, the system always resets over the winter. But what we're seeing since 2006 is a much greater correlation from one summer to the next, with quite a statistically significant correlation. So that's new. So we've seen an increase in persistence and an increase in variance, but we're also seeing an increase, a change in the spatial behavior of the sea ice. So Sian, I wonder if you could move along for me. Thank you. So this is a map image of sea ice anomalies where red is less than usual and blue is more than usual. And for two summers which had an overall low condition, December 2022 and December 1993. Now what you can see for the earlier period, 1993, there's less overall sea ice, but you can see that's marked by compensating regions. There's some areas where it's blue, there's a bit more ice, some areas where it's red. But what we've seen in recent summers, going back really until 2006, is a much more circumpolar change. So it's red almost everywhere. Now, that's part of the reason why recent summers have been so low, but it also marks out a change in how the sea ice responds to the rest of the physical system, and in particular in the winds. So most importantly, these three changes that have happened in the last decade or more, so an increase in variance, longer persistence, and a more spatially coherent pattern, these are all theoretical indicators of an abrupt critical change in the system. This is, as well as the really extreme statistic of this last event, this is one of the reasons why many scientists think the Southern Ocean may be shifting to a lower sea ice state. Now, although we can't detect an attribute specifically to greenhouse gas conditions, we can think about what this year tells us about our possible futures. Now, Sian, if you could move along. Thank you. So this is a rather busy and technical slide, but we can talk through it, and there's actually a really clear and very simple message to it. Now, what we're looking at here are sea ice extent anomalies against surface air temperature from 40 different climate model simulations. So each of those gray spaghetti lines is one climate model simulation. And so the black line on each panel is the average. And so that gives us an overall image of how sea ice will respond to a warmer climate or more surface air temperature. Now, the red dots are the satellite observations that we've already talked about. And there's some really clear messages here. First of all, compared to the models, this year's conditions are still pretty extreme. They're on the outlier of that spread of the grey dots, but they're not impossible under a 1.5 degrees C warming scenario. And this year was pretty close to 1.5 degrees Celsius. Above 1.5 degrees Celsius, you can see that the model indicates that sea ice loss increases rapidly, especially in winter. And actually, this year, what we've seen by 2 degrees C warming, this last winter would actually be the normal, shown by that approach to the black line. If you go back in time to a cooler climate, you can also see that those low red dots this year would be much less likely in a cooler climate. So what we're seeing is consistent with a warming global climate. And also note, although it's a slightly subtle change, the variability of the system, which is shown by the spread between the two dashed lines on each panel, it actually increases, that spread increases above a 1 degree C warming. And that, of course, is exactly as we're seeing in the observations. Now you can see one thing, which is the variability is a little different in the model and the obs. And it's important to note that the Antarctic and the Southern Ocean is one of the most difficult regions on Earth to model, in partly due to a lack of observations, but there's some really complex and unique processes going on there. And so there is a high uncertainty in how well the models capture these clear processes. But these climate models are the absolute state of the science, and they are our best tool for predicting Antarctica's future. And those models tell us something very clear. Above 1.5 degrees C warming, we will lose ice faster, and what we've seen this year and all its implications will be the norm under 2 degrees C. Now, if we can move on. Thank you. So in summary, my colleagues and I have presented evidence that shows just how important Antarctic sea ice is essential for the health of the Antarctic ecosystem, and it performs multiple climate surfaces that have global consequences for heat and carbon uptake and for sea level rise. And this is why Antarctic researchers all over the world, including this group, which represents 4 different nations across 3 different continents, we're so concerned about this very extreme year. For more information, you can follow the QR code to a briefing note called On Thin Ice. And also, I think Matt King, who's in the audience, has some hard copies if you're for in-person attendees. Now, it's important to note that whilst we cannot say for sure whether this year has been a response to climate change, we have seen multiple indicators of a potential regime shift over the last decade or more. And importantly, climate models indicate that whilst this year is a possible outlier under a 1.5 degree C warming, it will be the norm if we allow warming to reach that 2°C threshold. Antarctica is an irreplaceable ecosystem, and it is a critical component of the global climate. These extraordinary events of 2023 are a vision of Antarctica's future. It's not too late to act, though. We can mitigate the risk to Antarctica, but only if we keep global warming at that 1.5°C threshold. Even though it's the most remote region on our planet, a collapse of the Southern Ocean system will impact us all. Now, we're going to open the floor now to questions. And also, I'd like to introduce Nicole Hill, who will be joining the panel remotely from Hobart as well. And thank you for your attention.
Okay, so are there any questions in the room? Okay, so start off then.
Yeah, this is for any of you really, but I was wondering if you could comment on how much we can learn from what's happening and happened in the Arctic, and how much we can learn about what's happening in the Arctic and what's going to happen in the Antarctic.
Should we repeat the question for the online participants? Okay, so the question was basically how much we can learn from the Arctic for the Antarctic sea ice development that we currently observe. Will, do you want to comment on that?
I can make a brief comment. At face value, they seem like very similar systems.
Sorry, Will, we can't hear you currently.
Oh, okay. Can you hear me now?
You're online.
We can hear online.
Oh, you can hear online, just not in the room. Okay, well, so I suppose for online people, my response to the question is, although on the face of it, the Arctic seems very, very similar to the Southern Ocean, they are actually very, very different. One is an ocean surrounding land, and the other is land surrounding an ocean. And so the way that the ocean currents that affects the ice is very, very different. So
I can just play a thing like also on the phone. The ocean currents affects very, very different. Yeah, so I think
That's not live now.
I think just start again with the live.
Oh, okay. Can you hear me now?
But
No, but we still can't hear him. I think he said something, but
is it coming out of there or there?
yeah.
Maybe we'll just present again. Go back and present it.
Oh, can you hear me now?
Oh, that's
That somehow worked.
worked too well.
Wow, getting closer.
Okay, can you hear me now?
There's no way we can split out of that. You can't fit your head down. I don't know, guys. Yeah.
All right, we've switched our audio source. Do you mind giving another test or two, and we'll see if we've got you in the room?
Okay, testing from Hobart.
Right.
I think it says on.
Yeah, so this is the presenter laptop, yeah.
Yeah, maybe we should just do the questions.
Yeah.
Since the issues is really but difficult.
And so can they hear us now at least? Or can they just not? So what can you ask? Yes. Okay, so then we just like answer the questions in the room and then.
Yeah, and if they want to answer, we won't be able to hear them, but live streamers can. So that is one benefit.
The call valid before when we asked if we could.
So we continue forward.
Okay, so we'll just continue. Okay, so so I take your question, and so the question was whether we can learn the Arctic for the Antarctic sea ice. And from my perspective, I think this is kind of difficult because we do see that the underlying reasons might be different ones for the change in the sea ice covers for the Arctic and for the Antarctic. So in the Arctic, we do see that it's pretty much atmospheric driven, whereas when we look into the Southern Ocean, we have yet not a real clue. However, it seems like that it's more driven by changes in the ocean than in the atmosphere. And we also know that, for example, talking about sea ice extent evolution in general, this is also pretty much driven by winds, for example. And this is pretty different to what we observe in the Arctic. And one other factor is that when we look into the surface properties, which in the end really also determine how much energy is reflected or transmitted into the upper ocean. It's all about the snow cover. And looking into the Arctic sea ice cover, we have the seasonal cycle of snow properties where we have no snow at all during summertime, and but the formation of those melt bonds. However, when looking into the Southern Ocean, we have really a persistent snow cover which is barely melting throughout the seasonal cycle, and which therefore also again just underlines the importance of the ocean and the ocean heat flux from below than the atmospheric forcings.
Yeah, another interesting point I would deliver is that we had a very interesting international sea ice modeling workshop late October. And then we invited sea ice modelers, and then they said very interesting the studies that models developed by the people living in the northern hemisphere. So the Arctic models, and then the results are quite well. And then the thing is that the Southern Ocean is the Australia and the New Zealand very few people engaged in that the developing the sea ice, and then also the physics itself is quite different from the Arctic and the Antarctic sea ice. So it's really hard to directly apply that the Arctic model to understand the Southern Ocean. So it's really kind of all the stage to develop the model for the understanding the Southern Ocean ice, the sea ice. So it's really really right time to start, and then to collect more efforts to make that happen.
I could perhaps add from the ecosystem perspective that there are definitely things that we can learn from the Arctic experience, which is that the changes, as Steffi and Wang Sang both said, have been happening for longer and in a better defined way in the Arctic. So in some ways, the Arctic can be used as a model system for the ecosystem. And that is because we know that ecosystems in both polar oceans are intrinsically linked to the seasonal cycle of sea ice. So as that changes, we know that the ecosystem will change. What we don't know is about the specific details of those changes. So for example, in phytoplankton, the microscopic plants, they are likely to change the different species of phytoplankton that are there, but we cannot say for sure whether the total amount will increase or decrease. But what we can say from both polar regions is it's that the species that are more dependent on the ice will fare the least well as the ice is lost. So the most iconic species in the Arctic would be the polar bear. The most iconic species in the Antarctic, as I showed, would be the emperor penguin. And because these species are so reliant on the sea ice for their habitat, their feeding, completing their breeding cycle, they will suffer the most and are most at risk of extinction in this century. Whereas other animals that use these environments, perhaps seasonally, and are less reliant on sea ice, may fare just fine in a new, a new state with less sea ice, and some may even be winners of climate change. They may actually fare better. But both ecosystems will change fundamentally, and we don't yet understand how that will happen, and that's why we need increasing and continuing research efforts in both polar regions. Robbie.
My question was actually for Will, so yeah, it was a fairly boring question, so it might not be great for the live stream.
Amy, how are we doing on the sound?
We can have, we'll go ahead and keep talking.
I'm talking now.
Time for your boring question.
So my question is the increased persistence present in models as well as the increased variance? And also, what is the physical mechanism that you think underpins increased persistence in anomalies?
So the first question about whether the persistence is there in the models, it's a great question, and one I really want to answer next week when I have time to actually interrogate the models. That's a flippant answer, but it is actually true. It is something we really want to look at. I haven't looked at it yet. There may be someone out there who is. But because some of these ways of looking at those statistical changes are things we've never really done before until recently, so we just haven't gotten around to interrogating the models in those ways. Now, I think the second question was whether we have any ideas about why there is an increase in persistence. We got no shortage of hypotheses, but I can't tell you why. But what we do know is that that reset in winter that historically always meant that there was no persistence, that was always the wipeout. That's to do with the way that the sea ice production, and when it freezes, it produces salt that mixes up and create these really interesting mixed layer processes. But basically, that's what gives you or used to give, the reset every winter, because you'd swamp the surface with deep water that is what oceanographers called old. The water itself is the same age as any other water. It's just been under the surface for a long time. And so it's got no memory. So the implication is when you see that increased persistence, there must be something changing in how the sea ice is reacting, is responding with the ocean. What that is and how that's happening and what's driving it, that's an ongoing question.
Okay. Thank you. Any other questions?
What kind of field measurements would you say we need more to better understand the systems?
Yeah, I think we are just like on the way to come up with a new field campaign where we really aim to have a really comprehensive and interdisciplinary set of data. This is the so-called Antarctica in Sync project. This project is really based now really internationally, where we really aim to better understand the whole coupled climate system in the Southern Ocean, from land going into the ocean, the sea ice and the atmosphere. This project was just endorsed by UNESCO as part of the UN Decade for Ocean. And we are just right now like getting into the preparation phase, which will last until 2026, where we really aim to get all parties on board, to get all disciplines on board, to really have the opportunity to study the whole system in one time. And we then aim to have the actual phase on site, the measurement phase in 2028, 29, and then afterwards going into the analysis. So people might now think about mosaic of the Southern Ocean as we had it in the Arctic. However, this is of course not as it's meant to be. So it's really meant as a huge interdisciplinary effort where we bring different infrastructures into the Southern Ocean, where we want to combine like similar measurements at different points in time and space to really make it possible to describe the whole system in one.
So I've got a question. Oh, sorry, do anything?
Yeah, I was just going to add to the answer to that question to say that as observational scientists, we want to measure everything, everywhere, all the time. But of course, that's not possible. So we have to be very targeted in what we measure, when and where. And we've got a reasonable idea in the surface ocean of where the important places are and what the important times of year are. But I think we know very little or much less about that for the seafloor environment. So this is to set up Nicole, who's joined us online, to perhaps reflect on what measurements are really needed in seafloor and deep sea ecosystems, because I think there is a lot more work to do there than there is in the surface ocean, simply because it's more difficult and more expensive to do. So I don't know if Nicole, you want to come in there?
Thanks, Jan. Yes, definitely it's harder environment to see what's actually going on. And for that reason, we know less about sort of baseline conditions, let alone how things are or going to change. So that really relies on, it's also we can't not an environment that we can remotely sense from satellites, which makes it again quite difficult. So we actually need to get there, and we need to be deploying cameras and so on the seafloor to see what's there, and continue to do that over time to see how things are changing. And then, of course, link that back to what's happening with the sea ice and other oceanographic conditions.
So my question follows on from that, Nicole, to you. So we can start off mute. So are there areas of Antarctica where we do know what the impacts of sea ice loss? So the Antarctic Peninsula. So what's happening is in the seafloor communities in the Antarctic Peninsula.
Good question. So there are some areas where we're seeing, like Jan said, there's this real sort of trade-off between getting more food going to the seafloor. So you have some of these communities thriving. You get changes in the types of communities depending on the current flow at the seafloor. So if you have lots of current flow, you tend to get those lovely, beautiful, structurally complex communities. If you don't have much flow on the seafloor, you tend to get deposit feeders, so things like sea stars and so on. So depending on the relationship between how much food is coming to the seafloor and the currents, you can get changes in the community. But then in areas, particularly some of the shallow areas where we have icebergs coming through, when you get more of those come through, when we lose the sea ice, that has devastating impacts on the communities that you see on the seafloor. Does that answer your question, Matt?
Yeah.
And so, you know, that's around, we've seen that around the Antarctic Peninsula, we've seen it, you know, around the parts of the Weddell Sea, everywhere we've seen huge losses in sea ice and ice shelves.
One more question. This one's about sea ice volume. I know that sea ice volume is hard to measure in Antarctica, really hard. But on the other side, on the modelling side, are we making progress at modelling the volume? Or is it all frozen, excuse the pun, because we don't have enough observations?
People are looking at my screen, so I assume they want me to answer. I think you said it right. The second one, we have no idea. You know, I know what the models do, but I have no idea if that's correct. But actually, this feeds in very much to what Steffi and Sian and what Sang was saying is the critical need for observations to improve the models. We really need these coordinated field campaigns, and we need those campaigns to be planned in concert with the modelers, so that, you know, we're working together to get a system that can predict the future. That's really, you know, and that's happened a bit in the past, and it's great to see that it's happening more and more. But yeah, in answer to the question about volume specifically, I mean, the model looks great compared to the obs I've got, you know. Which isn't very many.
Yeah, okay, I got it. Since we are kind of like a copy type of question, so we have heard about RTCS changes now for a long time. So in a way, we have been probably focusing more on the Arctic so far, and we have been putting more efforts science-wise, maybe also communicating better to policymakers society. So since we are hearing about changes in Antarctic sea ice and in the Southern Ocean more recently, do you feel that we are a little bit behind, or how we are doing, or have we learned something from the Arctic experience in communicating those changes, the impact, and threat, and so on? And this is a question for all of you.
Yeah, that is really important, but difficult to answer for scientists. The thing is that, for my country, South Korea, we're really kind of interested in the climate change and how to tackle the climate change from now. But the thing is that Antarctica is really way away from our home, so it's really hard to convince them what's real impacts, and then is it threatening now, and then also other physics are really well linked together, and then it's really hard to instantly understand that's the immediate action or immediate response from the changes in Antarctica that's impact on our country. So the thing is that both the Arctic, the changes, for example, the polar jet or the sea ice changes will really impact right on the winter season in Korea. So many people are now getting to understand more than before. So the thing is that there are a lot of efforts between scientists and then general public. We have a lot of communications and then other meetings together. But still, for the Antarctica. It's a really big gap between. So we wanted to learn how to do that, and then we wanted to follow the path for the Arctic scientists, and then just like try to deliver our understandings and our observations and our knowledge to deliver to the general public, likewise the Arctic community as well.
So I would add to that. I agree. Also, coming from a nation that is a long way away from here, up in Scotland, it is more difficult to convince people that the Antarctic matters. But what many of us have been doing this week so far as part of the efforts with ICCI is to get the message out there that we're not focusing on the effects in Antarctica for their own sake of what they do to Antarctica, but it's about the global impacts of the Antarctic changes that are underway. So things like changing the heat balance of Earth, like Fonsang spoke about, sea level rise, impacts of polar ocean acidification on fisheries and food security. So whilst these changes are happening in the Antarctic and the Arctic, they really are global in their impacts, and ultimately their impacts on the human population. And I think most people would agree that the COP is about creating a world that is better for the human population. And the science that comes from the polar regions and the high mountain cryosphere is really critical in underpinning the decisions that we make to make a better world for the global human population, by limiting warming to within 1.5 degrees of the pre-industrial level. And the key message is that we have to stick within that limit. And if we start to push to 2 degrees or even higher, we are putting human society in peril. And that's what we want to avoid through the negotiations happening here. So the focus is on the impacts of the cryosphere on people, not just the cryosphere for the cryosphere's sake.
We actually have a question from online. I'm happy to read it out, otherwise we'll take it.
No, read it out.
So we've got, as far as I understand, the discussion has been about the extent of sea ice. Is the thickness or lack thereof? Yeah, so maybe I can take that on. So of course the thickness has a real big implication to understand the whole system better. But unfortunately, as it was already mentioned, I mean, even though we'll think thinks his model is doing great, we have no clue what is reality. Given the fact that we have really huge issues to determine the sea ice thickness from satellite remote sensing, given that we have no clue about the snow cover on top of it, and we have therefore huge uncertainties when looking on sea ice maps produced from satellite remote sensing, talking about sea ice thickness. And therefore, this is also one of the big gaps that we have to fill and that we have to understand better with future campaigns, both like combined missions on satellite remote sensing model and then the observations, because we do have, of course, some local observations from field campaigns. However, with those, we cannot really upscale them to the bigger picture. And therefore, again, this is one of the big reasons why we need this really collaborative and synchronous observations to really understand the whole system at once. Yeah, okay, so if there's no other question, I think we thank the audience here and the audience online. And we look forward to further interesting discussions today at the Sea Ice Day in the Cryosphere Pavilion. And yeah, I look forward to see you later again.